Hello everyone, I'm your instructor, Wang Shengdao. In this lesson, we'll be exploring the conformation, chain segments, and flexibility of polymers. By the end of this lesson, you'll understand the internal rotation of single bonds and master the concepts of conformation, chain segments, and flexibility. You'll be able to explain why single bonds can internally rotate. You'll be able to clearly define the concepts of polymer conformation, chain segments, and flexibility. You'll also develop strong communication skills. Polymers are giant molecules made up of thousands of repeating units, each similar in size to small molecules, linked together by covalent bonds. They're similar to iron chains you see in the real world. They can move and take on a wide variety of shapes in space. As you can see in the diagram, there are fully extended, straight chains. There are completely randomly coiled chains. There are also regularly bent chains, such as folded chains, helical chains, and others. So, what is the fundamental type of movement that allows polymers to take on so many different shapes in space? Most polymer backbones contain many single bonds, such as polyethylene, polypropylene, polystyrene, etc. The backbone is made entirely of carbon-carbon single bonds. These single bonds are sigma bonds. Their electron cloud distribution is axially symmetric, as shown in the diagram. Experimental evidence shows single bonds can freely rotate around their axis. This rotation does not affect the electron cloud distribution. This type of rotation is called internal rotation. A polymer chain has many single bonds. Every single bond can rotate internally at the same time. So, you can imagine that polymers can take on countless shapes in three-dimensional space. We refer to the various shapes a polymer chain adopts in space, due to the internal rotation of its single bonds, as the polymer's conformations. In other words, a conformation is simply the shape a polymer takes in space. We just used the specific term conformation for this. Different conformations of the same polymer chain are referred to as spatial isomers, as shown in the diagram. In fact, carbon-carbon single bonds are never completely free to rotate internally. That's because carbon atoms are always bonded to other atoms or groups. When these atoms or groups get close to each other, their outer electron clouds repel one another. This repulsion hinders the internal rotation of the single bond. Rotating requires a certain amount of energy to overcome the resistance to internal rotation. Let's use ethane, the simplest case, as an example. The diagram shows the trans and cis conformations of the ethane molecule. The repulsion between the two sets of non-bonded hydrogen atoms in ethane keeps them as far apart as possible. So the trans conformation has lower potential energy than the cis conformation. In other words, converting the trans conformation to the cis conformation by rotating around a single bond requires overcoming an energy barrier. In an ideal situation, all single bonds would be able to rotate freely. This means that a polymer can have an infinite number of possible conformations. However, actual polymer chains all have substituents, and the internal rotation of single bonds is restricted by bond angles. That is, internal rotation does not change the bond angles. Intramolecular and intermolecular forces also prevent free internal rotation. So, not every single bond can rotate freely. It also means that single bonds can't be considered the basic units for free chain movement. Actually, single bonds along a polymer chain restrict each other's internal rotation. When a single bond rotates internally, it inevitably causes the connected chain segments before and after it to move as well. A chain that is implicated, or, in other words, the portion made up of several structural units, can be viewed as a small unit on the polymer chain that can move independently. This small unit is called a chain segment. This leads to the definition of a chain segment: the smallest unit of a polymer chain that can move independently. As shown in the diagram, the black line shows the backbone of the polymer chain. The blue line shows the side branches of the polymer chain. The section of the polymer chain inside the pink circle is called a segment. It contains several structural units of the polymer chain. That is to say, all the single bonds within the pink circle, when undergoing internal rotation, will more or less cause the surrounding single bonds to move together. But this doesn't affect the structures outside the pink circle. The longer the segment, the fewer units on the polymer chain can move independently. The polymer chain can adopt fewer conformations. Imagine, if the segment length is about the same as the whole polymer chain, the polymer chain will act more like a rigid rod. The shorter the segment, the more possible shapes a polymer chain can take on. Chain segments are among the most important concepts in polymer physics. You'll see this concept come up repeatedly throughout the rest of the course. This brings us to the idea of flexibility, meaning how easily a polymer chain can change its shape. Flexibility comes from the internal rotation around single bonds. The degree of flexibility reflects the ease or difficulty of internal rotation of single bonds. That is, the better the flexibility, the easier the internal rotation of a single bond, the worse the flexibility, the more difficult the internal rotation of a single bond. In this lesson, we learned about the internal rotation of single bonds, the concept of polymer conformation, and the concepts of chain segments and flexibility.